Okay, it was suggested that I might have made a mistake by taking the drippings from an air conditioner for my quote distilled end quote water. So I went to Stop and Shop today and picked up a gallon of pure steam distilled water just to make sure that I'm not introducing any anomalies into the measurements that I'm taking. So here is the spiral cell again, sitting in pure distilled water this time. Alright, I got my leads coming down to the meter. I am on, and I can't zoom right now, I'm on the 2000 microfarad scale, and I am reading 1052 microfarads. So there actually is some effect with the drippings that I had collected from air conditioners. There evidently is some contamination in the water, so this is pure distilled, and yet it is still only half of what I measured with the air conditioner drippings. Okay, here I'm now connected to the ohmmeter input, and I'm on the 2K ohm scale. You can see right there. I'm going to switch the polarity of my leads in the meter, and I'm going to connect it now. And you can see it's behaving just like a charged capacitor, showing a negative resistance when I switch polarity, and it starts to climb. Now, the lower the scale on the meter, the higher the current I'm feeding into the cell, so the faster I should see it charging. If I go to a higher resistance scale, that'll actually go at a much slower rate, and eventually it goes off scale. Okay. Now, if I switch to 20K ohms, it's actually starting to drop. So once it has settled down, it looks as though my leakage resistance on the cell is about 6,000 ohms for 75 square inches of surface area in solution. Now it is climbing, so that's interesting. What is it doing? It's charging, obviously, like a capacitor. Why it dropped and then started to go up, I don't know. Perhaps there is some water circulation taking place, or maybe some water circulation has stopped. In any event, it's obviously not a static value. It only adds to the problem of trying to find and lock onto the resonance point and follow it.